Hello, everyone. I am James Beecham, founder and CEO of data security company Alter, and welcome to another edition of Rabbit Hole Reviews. This is a set time that I try to spend every week where I get to talk about some of the rabbit holes that I went down around security topics or data security topics in general, where a rabbit hole is defined as many open tabs from a single article or having to go pretty deep in Google or the chatbot systems to learn about a topic and hopefully save you all some time by going over it in kind of a review-like format here. So thank you very much for joining. As I have done in the past, I've been reading a lot about NIST lately, and came across their differential privacy framework that was just released, along with actually a framework around AI governance, and I believe even some around synthetic data. But going to talk about differential privacy today. Differential privacy is something that I had been familiar with, but never really dug into the math or the science behind it, or kind of what led to its advancement. And so that's kind of what led to this rabbit hole. Differential privacy is defined as a mathematical framework to protect the PII of data that is either shared knowingly for the purposes of collaboration or is taken unknowingly in the form of a data breach, for example. And started doing some research into kind of where this came from and kind of why it happened to be so. Found something interesting. In 1997, 87% of citizens of the United States could be identified with just three pieces of information: their gender, their zip code, and their date of birth. And so this realization started leading to the study or the understanding of how can we publish data sets for the process of learning, but maintain privacy of the citizens and the users within those data sets. I thought that was pretty high, 87% there. In 2003, there was a study done, and it was proven to be impossible to query private data without exposing at least some level of the underlying private information. So in that 6-year period from 97 to 2003, they worked on how do you query this data in such a way that you can maintain its privacy and not expose the information. And the answer was you can't. And that led to the fundamental law of information reason. And this law is well documented and well published. Then in 2006, we get a paper from Cynthia Dwork, Frank McStory, I believe, Kobe Nissim, and Adam D. Smith. Apologies if I mess those names up at all. Which essentially began to introduce what is now the modern differential privacy, and prove that mathematically you can query data that is statistically significant, but while keeping the privacy maintained. I had always heard of differential privacy as being a form of a PET, a privacy enhancing technology or privacy enhancing technique. So I did some research into kind of what those PETs are, what they look like. They're actually broken down into two major categories: soft privacy and hard privacy. The soft privacy is a little bit more what I'm used to and what I see every day. And soft means that the other side of the transaction, or whom you're sharing or giving the information to, is assumed to be trusted or has the ability to be trusted. And so therefore you can implement things such as access controls, differential privacy, and a few other techniques to ensure the privacy is maintained of that data. On the other side, hard privacy is defined where there is no single entity that is allowed to understand or can violate the privacy of the information. And the examples in this case are things like onion routers and VPNs, where you want to remain private from really any party of the transaction. So I started digging more into the soft side of the PETs, and learned that there's kind of two major categories as it relates to data. There's the data privacy enhancing technologies for transactional data or data processing, and then there's PETs or techniques for analytical use of data. So On the processing side, there's a number of techniques out there, zero knowledge proofs, FPE or format preserving encryption, which is something that allows sensitive information to be protected in a cryptographic way but maintain its format. So a phone number still looks like a phone number, an email address still looks like an email address, but the values are themselves protected. And then on the analytical side, the two major technologies in play are homomorphic encryption and then differential privacy, which is where this entire rabbit hole began, was NIST formalizing their framework for this. And I had heard of homomorphic encryption before. I know IBM was doing a lot of work with it. We've seen a lot of startups come out of the Bay Area around it. I think the promise of homomorphic encryption is to be able to operate and query encrypted information without ever having to decrypt that data, and I believe it was proven to work. But I think a lot of the challenges are around the scale and the cost of implementing such a technology. I've not seen anybody at scale or any large enterprise be able to adopt this in any meaningful way. Doesn't mean that it's not out there being used today, but I do know that it is difficult to operationalize. Differential privacy, on the other hand, is something that can be done relatively easily now with all the effort and the work. And so digging through the NIST framework for it, they go through all the background on the math and how to make sure that you have a good set of input data to produce a privacy preserved output set of data. Some of the suggestions in there are to not roll your own differential privacy, so use trusted or known libraries or leverage the technologies that are being provided to you by your data providers or your data sources themselves. I know the large analytical engines like Snowflake and Databricks and others have either made acquisitions or have developed their own features. But if you're using this for more processing type of data systems, please leverage the open source repositories or the information that NIST has published into their own GitHub, which you can find just by typing in NIST space GitHub space differential privacy in there. So hopefully that gives you a little bit more information about differential privacy. The fact that NIST has a framework on it here means that we are going to be seeing more and more of this in the form of data sharing and data collaboration. It's used in public sector as well as in the private sector. So hopefully you learn a little bit more about differential privacy. If you want to dig into the math, it's actually relatively simple, even though it looks complex at first. So go take a look. Hope you all have a good day. Thank you so much for tuning in.